Have you ever wondered what actually powers a ship carrying 6,000 passengers across an ocean, using more fuel in a single day than most cars burn in a decade? Most people assume it's some form of diesel, refined, clean, ready to pour straight into an engine. The truth is stranger. The fuel sitting in a cruise ship's tanks, before it can be used at all, has to be heated until it stops behaving like a solid. The answer sits somewhere between industrial waste product and precisely engineered solution, and understanding it changes how you look at everything happening below deck on a ship this size. To understand why, we need to look at where this fuel actually comes from. When crude oil is refined, it's heated inside a fractional distillation tower, and different components boil off and separate at different temperatures. The lightest fractions rise first: gasoline, naphtha, the fuels used in cars and small engines. Kerosene and diesel condense further down. But at the very bottom of that tower sits the heaviest, thickest material of all, the residue left over once everything lighter has already been extracted. That residue is called heavy fuel oil, and it is, for most large ships still operating today, the primary fuel burned to cross the ocean. Heavy fuel oil is not a clean, refined product. It is, quite literally, whatever is left when the refining process is finished, taking everything more valuable out of the barrel. Its boiling range sits between roughly 350 and 500 degrees Celsius, dramatically higher than gasoline or diesel. And that high boiling point comes with a side effect almost nobody outside the shipping industry knows about. At room temperature, heavy fuel oil doesn't pour. It doesn't even really flow. It sits closer to cold tar or hardened pitch, a thick, dark, semi-solid mass that has to be physically cut or scooped rather than poured from a container. The term itself comes from an older era of shipping entirely. Steamships once stored their coal in dedicated compartments called bunkers, and when oil eventually replaced coal as the standard marine fuel, the name simply carried over. Bunker fuel became the general industry term for whatever a ship burns, and heavy fuel oil, sometimes labeled Bunker C in older grading systems, has remained the most common version of it for well over a century. That shift from coal to oil didn't happen gradually or by accident. Winston Churchill, then serving as First Lord of the Admiralty, pushed the British Royal Navy to convert its entire battleship fleet from coal to oil power in the years just before the First World War, a decision made specifically because oil-fired ships could travel faster and refuel far more quickly than coal-fired ones, which had to be laboriously loaded by hand. Commercial shipping followed the same logic in the decades after, and by the mid-20th century, oil-based fuels had almost completely replaced coal across the entire global merchant fleet. That creates an immediate engineering problem. A ship's engine needs a continuous, steady stream of liquid fuel to run. Tar does not move through a pipe on its own. So before heavy fuel oil can be pumped anywhere inside the ship, let alone injected into an engine, it has to be heated, typically to somewhere between 50 and 65 degrees Celsius just to become fluid enough to move through the piping, and heated further still, sometimes above 100 degrees, immediately before injection into the engine itself to reach the correct viscosity for proper combustion. In technical terms, heavy fuel oil is sold and measured by viscosity, most commonly graded at 180 centistokes or 380 centistokes, numbers that describe exactly how resistant the fuel is to flowing. For comparison, ordinary diesel measures in the low single digits on that same scale. A fuel rated at 380 centistokes is roughly 100 times thicker than diesel at the same temperature, which is the actual, measurable reason it behaves more like a solid than a liquid until it's heated. This is not a minor technical footnote. It shapes the entire design of a ship's engine room. Fuel storage tanks are built with internal heating coils running through them, keeping the bulk supply warm enough to stay workable. Pipes carrying the fuel toward the engine are traced with their own heating elements, essentially running a secondary layer of plumbing whose only job is preventing the fuel inside from cooling back down and solidifying mid-transit. Before combustion, the fuel passes through purifiers and centrifuges that spin out water, sediment, and other contaminants that settle naturally in a product this crude and unrefined. None of this happens with a fuel like diesel, which flows freely at ordinary temperatures and requires none of this dedicated heating infrastructure. Some heavier grades require even more aggressive heating, up to 120 or even 150 degrees Celsius, before they reach the thin, easily atomized consistency, and engines' fuel injectors actually need to burn it cleanly and efficiently. The purification stage matters more than it might sound. Heavy fuel oil straight from the barrel can carry water, catalyst fines left over from the refining process, and other abrasive particles that would rapidly damage an engine's precision components if they weren't removed first. Centrifugal purifiers spin the heated fuel at high speed, using the difference in density between the oil and its contaminants to separate them out before the fuel ever reaches the engine's injectors. To put a real number on that daily burn, a large modern cruise ship can consume somewhere in the range of 250 to over 300 tons of fuel in a single 24-hour period at cruising speed, depending on the ship's size and how fast it's traveling. Multiply that across a week-long voyage, and a single ship can burn well over 1,000 tons of fuel before it ever returns to its home port, a scale that makes even a modest per-ton price difference between fuel types translate into real money fast. For comparison, an ordinary passenger car might burn through a single tank of gasoline in a week or two of regular driving. A cruise ship burns the equivalent of thousands of those tanks combined every single day, just to keep the lights, engines, and air conditioning running for a floating population the size of a small town. So why would any shipping company choose a fuel this difficult to work with in the first place? The answer comes down to cost and energy density. Heavy fuel oil is significantly cheaper than refined distillates, commonly cited at around 30% less expensive per ton than marine gas, oil, or diesel. For a vessel burning well over 100 tons of fuel a day on a long crossing, that price difference compounds into an enormous operating cost advantage across a single voyage, and an even larger one across an entire fleet operating year-round. Heavy fuel oil also carries a high energy density, meaning a relatively small volume delivers a large amount of usable energy, which matters enormously when a ship needs to carry enough fuel to cross an ocean without needing to refuel partway through. Across an entire fleet running dozens of ships year-round, that 30% gap compounds into a difference of tens of millions of dollars annually, money that goes straight to the bottom line of a cruise line's operating budget rather than to fuel suppliers, which explains why heavy fuel oil remained the default choice for so long, despite every engineering complication it introduces. But heavy fuel oil comes with a cost beyond the price per ton, and that cost is measured in sulfur. Because it is the residual product of refining, heavy fuel oil concentrates many of the impurities originally present in crude oil, sulfur chief among them. Burning it releases sulfur oxide emissions at levels far higher than cleaner fuels, a genuine environmental and public health concern that international regulators eventually moved to address directly. In 2020, the International Maritime Organization implemented what is now known simply as IMO 2020, a global regulation capping the sulfur content of marine fuel at 0.5% by weight, down sharply from the previous limit of 3.5%. Inside specially designated emission control areas, the limit drops even further, to 0.1%. That single regulatory change forced the entire global shipping industry, cruise lines included, to make a decision. Comply by switching to lower sulfur fuel entirely, or keep burning the cheaper heavy fuel oil and install additional equipment to clean the exhaust before it leaves the ship. Those stricter emission control areas cover some of the busiest cruise regions on the planet, including the waters around North America, the Baltic Sea, and the North Sea, which means a single ship crossing from open ocean into one of these zones may need to switch fuel type entirely mid-voyage, a routine but genuinely complex operational procedure that has to be carefully timed and managed by the engine room crew. There's an underappreciated safety dimension to heavy fuel oil's thickness too. Its high flash point, the temperature at which its vapors can ignite, sits well above that of lighter fuels like gasoline or diesel, meaning it's considerably harder to accidentally ignite in normal handling and storage conditions. A fuel this viscous simply doesn't produce much vapor at ordinary temperatures, which is a genuine safety advantage buried inside what otherwise reads as pure engineering inconvenience. Many operators chose the second path, installing what are known as scrubbers, exhaust gas cleaning systems that strip sulfur oxides out of the smoke before it exits the funnel, allowing the ship to keep burning cheaper heavy fuel oil while still meeting the new emissions limit on paper. A single scrubber installation can cost several $1 million per ship, a significant upfront investment, but one that pays for itself relatively quickly given how much cheaper heavy fuel oil remains compared to the alternatives. The trade-off is genuine, though. Scrubbers work by washing exhaust gases with seawater, and the resulting wastewater, now carrying the sulfur and other contaminants stripped from the exhaust, is in many designs discharged back into the ocean. Several jurisdictions, including Hawaii and California, have restricted or banned that discharge specifically because of concerns about what it does to marine ecosystems, forcing ships operating in those waters to switch to cleaner fuel while transiting through instead. Industry estimates place the number of ships worldwide that had installed scrubbers by the early 2020s at several thousand. A small fraction of the global fleet overall, but a large enough share of major cruise and cargo vessels that the debate over scrubber wastewater discharge has become one of the more contentious environmental fights inside the shipping industry, pitting the financial logic of cheap fuel against genuine questions about long-term ocean health. The alternative path is switching to marine gas oil, a lighter, cleaner distillate fuel chemically closer to ordinary diesel, or moving further still to liquefied natural gas, which contains essentially no sulfur at all and burns dramatically cleaner across the board. Several major cruise lines have committed to building new ships specifically designed around LNG propulsion, accepting a more complex and expensive fuel storage system, since LNG has to be kept cryogenically cold in specialized tanks, in exchange for a fuel that sidesteps the sulfur problem entirely rather than managing it after the fact with a scrubber. Storing LNG requires specialized tanks capable of holding fuel at roughly -160 degrees Celsius, the temperature at which natural gas becomes a liquid dense enough to carry practically aboard a ship. That's a fundamentally different engineering challenge than heating heavy fuel oil to keep it flowing. Instead of fighting a fuel that wants to solidify, LNG systems fight a fuel that wants to boil off and escape as gas, requiring heavily insulated containment systems that add real cost and complexity to a ship's design from the very beginning. What ties all of this together is a fuel that was never actually designed for the job it's doing. Heavy fuel oil exists because refineries need somewhere for the leftover residue to go once every more valuable fraction has already been extracted from a barrel of crude oil. The shipping industry adopted it because it was cheap, energy-dense, and available in enormous quantities, not because anyone set out to design the ideal marine fuel from scratch. Every heating coil, every traced pipe, every purifier and centrifuge running quietly in a cruise ship's engine room exists to compensate for the fact that the fuel itself would rather be a solid than a liquid. It's a strange kind of engineering triumph, building an entire supporting system around a fuel's flaws rather than solving them, because doing so remains cheaper than switching to something that wouldn't need the workaround in the first place. In other words, the fuel powering a modern cruise ship across the ocean is not simply oil. It is a substance engineers have had to build an entire supporting infrastructure around, kept warm, kept moving, kept clean enough to burn, purely so a ship the size of a small city can keep crossing oceans on the cheapest fuel available, one that would otherwise sit as inert as asphalt in the bottom of its own tanks. There's another resource on board that gets engineered around just as heavily, though for the opposite reason. A ship carrying thousands of people needs an enormous, constant supply of fresh water, and the surprising truth is that almost none of it is actually stored on board at all. Subscribe to find out where a cruise ship's drinking water really comes from, and why the tank most passengers imagine barely exists.